So this video is going to go over using Euler's method to approximate the solution of differential equations. And you probably already have a good idea of what a differential equation is. It's just an equation that relates one or more functions and its derivatives to each other. And the solution for these is going to be a function or a set of functions. Like, you've already done stuff with integration, so I already know the solution for this differential equation is going to be like y equals whatever, not a number of x or y. And you probably already know how to solve some differential equations like the first one. You just integrate both sides. But it becomes harder to solve differential equations as once you get like more types of them. Like for example, the second one. This one, you can't just integrate both sides because you have both x and y. And some more terminology is that Euler's method only really works with first order differential equations, which is differential equations that just have dy over dx or f prime of x or just one derivative. And this is an example of something that's not first order, that has this derivative or the second derivative of y. And Euler's method only works with the first derivative, first order differential equations. So let's have a problem using Euler's method. And when you use Euler's method, you are finding the value of your solution at a certain point. So for this one, it's the value of y at a certain x value. And in this we're going to find y of 1, or y at x equals 1. And we're given that y of 0 is equal to 0.5. So Euler's method calculates it like, not exact, but it uses steps, kind of like Riemann sums, but not really. The n is your step number, and it just like goes in increments. And basically h is your step size. And this one is 0.2, which means we're going up by 0.2 each time. And as your step size gets smaller, your approximation gets better. So if h was like 0.01, then you have to do more calculations, but your approximation would be better. So y of n plus 1, and again, n is a step number, is equal to y of yn plus h times f of x comma y. And f of x comma y is just like your derivative. So f of x y is going to be dy over dx is equal to x plus 1 minus y in this case. Yeah, so just rearranging it. And then xn plus 1 equals xn plus h. And that's pretty intuitive. The next step is just the previous step plus the step increment for your x value. And the y is that, but dependent on your function of the derivative. So let's replace f of x comma n, f of x comma y with our derivative. So x plus 1 minus y, like that. And now, if you don't have a calculator, you would need to do something like this. Step n, and then x of n, y of n. You start at n equals 0, which is just at 0 is 0.5, and then you go up by 2 each time, which means that at the first step, your x is 0.2, and your y is whatever this is, you plug in that, and then second step, 0.4, and then you keep going until x is 1, because you're trying to find when y equals, what y is at x equals 1. Now, I'm not going to do the table thing for now, but hopefully you understand how to do that. I'm going to do it on the TI-84. So first, what you're going to have to do is change your mode from function to sequence. And then that makes it so that when you press y equals, you have this thing here. So, and then change it to sequence n plus 1, because here we have y of n plus 1. And then your minimum is 0 because that's what you're given. Your minimum step is the 0th step with your initial value. And we're going to have u of n plus 1 be equal to x and v of n plus 1 equal to y. So we can use this formula x of n plus 1 equals x of n plus h. So to get u of n, you press second and then 7 to get the u here. And then you have to have your of n, so parentheses, and then you can click this xt theta n to get the n, plus 0.2 because that's our step size. And then your initial x value is 0, so you have u of 0 is equal to 0. U of 0 is just your initial value for x. And then v is your y, so v of n plus 1 is equal to v, you get second and then 8 to get the v, and plus 0.2 multiplied by this, which is u of n minus, or yeah, plus 1 minus vn. And again, u of n is your x, and v of n is your y. So, and then you put in your initial y value, and then you can click table, and then everything pops up here. And to get your desired value, you just check the u column because that's your x values. In this one, we're trying to find when x equals 1, so you just find when x equals 1 right here, and it's 1.16384. You can just write it into 3 sig figs, so 1.16 is your final answer. So again, what we did in this problem is first isolate dy over dx, and then use this information. We're finding y when x equals 1, our step size is 0.2, and y of 0 is equal to 0.5. To use these formulas, and then we plug them into our calculator using sequence mode, and then we press table, and then we found our value. Our approximate value is 1.16 for y of 1. Now let's get into some practice problems. If you think you can do this one, then pause the video and try it. This one says use step size 0.1 to estimate y of 1, given that dy over dx equals 1 plus 2x minus 3y, and y of 0 is equal to 1. So our formulas, just plug in everything we know. So y of n plus 1 is equal to y n plus h, which is 0.1 in this case. And then our f of x comma y, which is dy over dx, so 1 plus 2x minus 3y. It's already isolated. And then our x of n plus 1 is equal to x of n plus 0.1. And now we put everything into the calculator. Remember to switch over to sequence. Go here, switch to n plus 1, your min value to 0, and then u of n plus 1, this is your x, which is u n plus 0.1. The initial value is 0, and then our y is v of n plus 0.1 times 1 plus 2x plus 3y, so 1 plus 2 times u of n minus 3 times v of n, and then our initial value for that is 1. And then we go to table, and then we go to where we need y of 1, which is when u equals to 1, and that value is 0.803. So 0.803 is our final answer for this problem. Now let's do one last practice problem. If you think you know how to do this one, then pause the video and try it. This one says use step size 0.01 to estimate y of 2 given dy over dx equals x times cosine y, y of 0 equals 0. And first we write our formulas. Y of n plus 1 is equal to y n plus h times f of x and y, and h is 0.01, and our f is our dy over dx, which is this. So we plug those in, 0.01 times xn cosine yn. Then our xn plus 1 is equal to x of n plus h, and our h is 0.01. So this is what we have, and then we just plug this into our calculator. Remember, change the mode to sequence. Press y equals, change the type to n plus 1, and change the minimum to 0. And then our u is our x, so it's going to be u of n plus 0.01. Our initial value is 0. V of n plus 1 is the n plus 0.01 times u of n, because that's our x, times cosine of, not our cosine, cosine of y, which is Vn. And then our initial value for that is 0. And then now, when you press table, you're going to get a lot of values before you reach u equals 2, which is what we're trying to estimate. So instead of just scrolling down a bunch, what you can do is you go to Window and change n to max to whatever value you need to calculate first. So since we're going by increments of 0.01, to get to x equals 2, you're going to need to do 200 steps. So set this equal to 200, or you can do more than 200, like 201, but 200 is fine. So 200 as your max. And then what you do is press second, calc, value, and then just wait for it. Enter the value you need. This time is 200. And then it's going to give you y equals 2, and that's your x value. And you can check that to double check that you're at the right one. This is right because we're trying to estimate when x equals 2, and this one says it's 2, and then you just press up or down to find the other value. So right here, this is our v, or our y, and the value is 1.3017. So in 3 sig figs is 1.30, and that is our final answer. So everything that I explained in this video and all of the problems that I went through should give you a good introduction on how to use Euler's method to approximate solutions for differential equations. If you learned something from this video, or if you enjoyed it, then please consider liking and subscribing.